Hello class, this is a video tutorial on the Generalized Pigeonhole Principle. To compare this, let's take a look at what we saw in the previous video. In the Pigeonhole Principle, we learned that if there was n plus 1 objects and there are only n number of positions, then at least one position must have two or more pigeons or objects. And we saw this demonstrated with 9 positions and 10 objects, and that when we fully saturated or filled up the 9 positions, we had one remainder that had to go into at least one of the positions, and that fulfills this pigeonhole principle. Okay, and we saw that demonstrated here with the different examples. In this one, this is kind of a reversed version of this. What this says is if we have n number of pigeons and they are to be placed into k number of pigeonholes positions, and n is greater than k, meaning the number of objects is greater than the number of positions, then at least one pigeonhole must contain n divided by k pigeons or objects. In the case of discrete objects, n divided by k is often rounded up or down according to the problem that we're facing. So let's see this in action and how we might apply this concept into these problems here. So a group of 75 people are organized into 4 teams. One team has at least X number of people. Find X. Well, in this case, if we were to try and simulate this, here are the 4 teams. And if we were to start filling them in with 75 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. One of these must have X. And this is assuming that we're trying to even out these 75 people into the 4 teams. Let's now apply this generalized pigeonhole principle. We have 75 people or objects divided by the 4 teams. Let's take a look at what we get. 75 divided by 4, 18.75. Whoops. So that means if we try to keep the number of people as evenly distributed as possible into the 4 teams, each team should get 18.75 people. But as you know, that's impossible to do because you can't get 0.75 of a person. So we round up and we get 19 people. That there is actually this pigeonhole principle in action. That means one of these teams, or at least one of these teams, must have 19 people in them. So let's take a look at what would happen. So we take 75 and let's take away that 19. We get, I believe, 56. 56. And if we do 56 divided by the 3 remaining teams, let's take a look at what we got. We got 18.6. Well, as you can see, so let's say there were 19 people in this one. There can't be 18.6 people in each of them. That means that there's another team that should have at least 19. But in any case, what the generalized pigeonhole principle states is that at least one of the teams, right? So it could be 1 team, 2 teams, or 3 teams, or all 4 of them, must have at least 19 people in them. So one team has at least X people. One team must have at least 19 people. And there's the problem. Okay, so let's move on. In a group of 117 people answering one of 5 questions, at least Y number of people answered the same question. Okay, in the exact same way. So here, let's make boxes for our questions. Here we are. 1, 2, 3. I believe that should make 5. There we go. 1, 2, 3, 4, 5. Here are our 5 questions. And if we were to try and populate this as evenly as we can with 117 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. One of these questions, or more, one or more of these questions have been answered by a certain number of people that are the same. Using the generalized pigeonhole principle, 117 divided by 5, we get 117 divided by 5, we get 23.4. In this case, we're going to round up because you can't have 23.4 people, right? So Y is 24 people. So that means at least one of these questions has 24 people who answered the same answer. So it could be one of them having 24, it could be 2 of them having 24, or it could be all of them who have 24. But at least one of them has 24 people who answered the same question. One last one here. A certain number of people had to be transported on 5 buses. At least one of the buses had 33 people on them. What range of total people were transported? Assume that the number of people on each bus was kept as low as possible. Similarly, again, we had the 5 buses. Let me just grab this illustration here. Here are the 5 buses. This time we don't know. We don't know how many people were being transported. So the total is, we don't know. We'll let the total be K. But we know we have 5 positions. 1, 2, 3, 4, 5. So the positions, or K, actually we should make the total be N to be consistent with the pigeonhole principle. And the position, K, is equal to 5. We have 5 pigeonholes. So we know that N over 5 is giving us 33. Okay? Now, N, if we just do some simple math, that's 165. Now that's assuming that all of them have 33 people. So 33, 33, 33, 33, and 33 by multiplying by 5, we're assuming that all of them had 33 people. But it says here that at least one of the buses had 33 people on them. At least one of them. That means at the very minimum there could be 32 on these ones. Whoops. And 33 on one of them. So it could be 32 times 4 plus 33, which if we use the calculator, 32 times 4 plus 33. So at the minimum, 161 people is the absolute minimum of the number of people which we don't know. So it says what range of total people were transported. It could be from 161 is less than N or is greater than or is less than 165. This is the range of people that could have been transported in this scenario. So, I hope that gave you an insight into the generalized pigeonhole principle. And yeah, hope to see you in the next video. Best of luck.